Hi, so I'm Paul Marinescu, and together with colleagues from Facebook and from CMU, I'm going to talk about Facebook's ongoing experiment into defense in depth against authorization bugs. Invariant Detector is currently running at Facebook, and it's looking for patterns in all the changes that are made to Facebook's social graph. Once it's confident that such a pattern is actually invariant of the system, it starts enforcing it, by which I mean that it starts blocking all the requests which break the pattern. And to get this out of the way, when I say social graph, I mean the entire Facebook database, not just people and their friendship relationships. And I think it's easiest to understand what Invariant Detector does and how it does it using an example. So I picked an actual bug that was reported some time ago to us by a white hat researcher, show you the details of the bug and how Invariant Detector would have helped automatically mitigate it. So this has to do with video comments. Video comments is a feature that was added to Facebook some 1 year ago, and it allows people to comment with videos. And internally, this was implemented as a two-step process. First, the user would take the video, upload it, and the system would assign an identifier to it. Then, in step 2, all the elements that are related to the comment are connected together. The post on which the comment is made is connected with the comment, and the comment is connected with the video. And I mean connecting in a very literal sense, because this is a graph and the connections are just edges in that graph. So the problem here was that a malicious user could have skipped step 1 and instead provide the identifier of an existing video in step 2 and using a crafted HTTP request. And the system would happily use that identifier, essentially allowing people to comment with other people's videos. That in itself wouldn't have been a big problem because privacy restrictions were still in place, so you couldn't see someone else's video if you wouldn't have the right to see it in the first place. The problem was that deleting the comment would trigger the deletion of all its associated content, which in this case was the video, which, as I was just saying, could have been someone else's video. The part that I wanted to get at is, in fact, the bug fix, which is very straightforward. Only allow connecting comments with videos if they have the same owner. And this is an invariant in the sense of invariant detector. It's the type of invariant that we can automatically learn and then enforce. How would this have worked? Well, invariant detector, IVD, sits on top of the social graph and sees every change that is made to the graph. Now, once video comments started to be tested internally and then during the initial rollout, it would have started to notice that comments are being connected with videos. And whenever that happened, both the comment and the video had the same owner. And once enough people would have done this, it would have concluded that this is an invariant of the system. And later on, when a malicious user would have tried to exploit the bug, they would have been automatically stopped by this invariant, which would have been already there. And there are a few things that I could tell you about invariant detector, but because we're short on time, I'm just going to talk about one aspect, the thing that I believe was the biggest challenge when building the system, and that's the most interesting part of invariant detector, the scale, the large scale at which it needs to run. And to give you a better sense of the scale, let's look at some numbers. We're talking about a graph database that has many trillions of entities, nodes, and edges, and to which more than 10 million changes per second are being made at peak time. And then we're talking about more than 200,000 invariants that have to be checked. And this creates some problems or challenges, depending on your point of view. And identified three categories, which I'm going to discuss during the rest of this presentation. First, we need to keep the overhead of checking these invariants low. Checking the invariants has to be done synchronously with every request because we have to decide right then whether we want to allow the request to proceed or not. Then we have a challenge related to learning the invariants. The size of the learning corpus for the invariants is really high. And then we have to mitigate false positives, which are inevitable when we learn invariants based on a limited number of observations. So I'll start with the first, of course. And our solution to keeping the overhead low is to have a lightweight invariant design. And this design is, in fact, the cornerstone of invariant detector. It's a design that allows invariants to be quickly checked and enforced. It makes learning tractable and not to be underestimated. It makes the invariants easy to understand by a human, by an engineer who's investigating a report. And to understand how we got to this design, it's important to remember that invariants are nothing but authorization rules. And it turns out that in a system that structures its data as a graph, authorization rules are relationships between the objects in the graph. In other words, they're paths in the graph. And our insight, invariant detector's insight, is that most authorization rules are really short paths in the graph. So with this observation, we created a design that limits the number of objects that can be involved in an invariant. It limits them to the objects which are involved in the change that's being looked at, like the comment and the video in the previous example. The properties of these objects, like their owner, and a small set of global objects which are relevant to authorization and are domain-specific, like the currently logged-in user, the groups that they're the administrator of, and the groups that they're a member of, their pages, their friends. And with this restriction, checking the invariants is really fast. In fact, invariant detector is using just 0.014% of all the CPU that the code running on our web servers use. And the overhead that it adds to each request is virtually imperceptible to a user, to an end user. Moving on, I already hinted that this design helps with learning because it's so lightweight or simple. But we still have a problem. The size of the learning corpus is pretty big. I should tell you at this point that we don't learn invariants in real time, but instead we use an offline process. We have a daily process which learns or relearns invariants based on all the requests from based on the requests from the previous day. And this is a lot of requests, which not only we cannot handle in the learning process, but we don't even want to store all these requests so we can later look at them. So what we do instead, we carefully sample a subset of these requests. And the intuition is that learning on the subset will, in fact, give us an over-approximation of the invariants, a superset of the invariants. We'll introduce some false positives. And to deal with the false positives, we don't directly start to evaluate, to enforce the invariants, but we put them through a learning process, through an evaluation process, which means that they're checked against all traffic, that all the changes that are made to the graph. But whenever they're broken, they don't block the request. Instead, they get deleted because most likely that wasn't an invariant in the first place. So only the invariants that go through this evaluation period without ever being broken end up being ratified and enforced. And this allows us to learn the invariants and also takes care of some of the false positives. But it turns out that we need to do more in order to bring false positives to a manageable level. And we have a few additional techniques. Of course, we have manual invariant blacklisting, where an engineer, usually as a result of a report, comes and manually deletes an invariant. But we also have what we call enforcement excuses. These are rules which get evaluated at runtime whenever an invariant gets broken, and give the request one more chance to continue. So I've shown you how we learn the invariants in this two-step process. Now, when an invariant is broken, the runtime excuses have one more chance to give the request one more chance to proceed. Only if none of them excuses the request, then it's blocked, and that sends a notification to an engineer. The type of excuses that we have are largely domain-specific. Some of them deal with requests made by internal tools or internal bots, which are quite unlikely to be malicious. Other excuses have to deal with aliasing. In our system, it's quite possible that the same entity can be referred to by different identifiers. For example, a user may have their personal persona, their business persona, their advertiser persona, but they all boil down to the same entity as far as authorization is concerned. And then we have corner cases like memorialized accounts. And then we have subtle differences between different surfaces of the Facebook product, like differences between regular Facebook and Facebook for Business. And it turns out that with these runtime excuses, we get the false positives to a manageable level. And if I were to put everything into perspective, all the false positives discussion into perspective, it would look something like this. 2/3 of them are handled by the two-step invariant learning. About 99% of the remaining false positives are handled by the manual blacklist that we have accumulated over time. 99% of the remaining false positives are handled by the enforcement excuses. And what's left, which is a small fraction of the original false positives, is something that's manageable for us. In fact, the system's overall false positive rate is really, really small. And with this, I'm gonna conclude. And if there's just one thing that you're gonna remember from this presentation, make that be that invariant detection is a tractable defense in depth at large scale. And this has mitigated actual bugs at Facebook, previously unknown actual bugs at Facebook. Questions?
Hello, Tomasz Kuchta from Qualcomm. Thank you for the talk. I was actually wondering, could you please comment on how easy that would be for a coordinated group, like large group of people, to influence invariants in such a way that the behavior that will be treated as invariant will be actually invalid, something wrong, to skew the invariant to their way? Thank you.
I don't think that would create a valid attack. So first of all, to have an invariant, that operation must be allowed by the code in the first place. because the database request must reach the database. If that's some malicious behavior, then the code would already reject it, the behavior of the group of coordinated people. So I don't see how that would, how they would be able to manipulate the system unless the system is already faulty.
So you finished with a wonderful teaser that you mitigated actual bugs, but you only opened with an example of a white hat who told you about a bug and that you're able to find. So could you give us an example of an actual bug?
Yes, actually, there's a case study section in the paper where we present some actual bugs which are presented for the first time. One other bug that was mitigated had to do with transforming a personal profile into a page. Facebook has this feature where a personal profile, which doesn't really represent a person, can be transformed into a page in order to be in compliance with Facebook's rules. And as part of that process, all the friends of the personal profile are transformed into fans of the page. And again, this is a two-step process because the profile, the page object is created and then the fans are transferred to it. And quite similarly to the example that I gave, an attacker could have crafted an HTTP request that only triggers the second step of the process to transfer friends to their existing page, essentially gaining fans for free.
Thank you.
Okay, thanks for coming. That's it for this session.